name's Kelly, and today we're going to be talking about enzyme kinetics for the general catalysis equation above. So it's really important to realize that when we talk about enzyme kinetics, we're not talking about the way the velocity of a reaction changes over time. We're talking about the initial velocity of the reaction. So what I mean by that, you can see this graph here on the left. It shows change in product over time. So initially, at the very beginning of the reaction, we're going to have this huge increase in product and slowly start to diminish the formation of product. So if you think of that in terms of velocity, as the reaction proceeds, the velocity of the reaction is going to slow down. But that's not what we're discussing. We're only discussing initial velocity of the reaction. So you're going to become really familiar with this graph, and you need to understand that we're only discussing what the velocity is right at the beginning. So when we're looking at enzyme kinetics, we have to make two assumptions. The first assumption is the equilibrium assumption. Here we're saying that K2 is a lot less than K to the negative 1. By this we mean that product formation is a lot slower than ES dissociation back into ES. So what does that mean? Essentially, we can just say that we reach equilibrium in the first part of the reaction very quickly. So when we reach equilibrium, we know the velocity of the forward reaction is equal to the velocity of the backwards reaction. Here, I just plugged in the correct substrates on the appropriate side, and using this, they made the dissociation constant. It's important to realize that the dissociation constant is an equilibrium constant, and by that we mean that it describes the relative amount of substrate and product at equilibrium. So if you can see here, we have Kd equals enzyme and substrate all over the enzyme-substrate complex. So I like to remember it as this is dissociated because they are not together, and this is the associated form. So it's really dissociation over association. So if you want to think, do I want a low Kd or do I want a high Kd? Well, you're really going to want it to be in the enzyme substrate complex more than you're going to want it to be dissociated back into the unbound form. So really, if you thought about it, you would think, all right, well, I want that to be low and I want that to be high. So essentially, you want a lower Kd. So our second assumption is a steady state assumption. When we say we're in a steady state, all we're saying is that the concentration of the ES complex is constant. So for it to be constant, our ES formation needs to equal our ES loss. Because the probability of product going backwards to substrate is so low, we can take K to the negative 2 out of our equation. So we won't consider that for ES formation. So here's just an equation that shows you ES formation equal to ES loss. So I redrew our general catalytic reaction below to help you guys understand where we get the initial velocity equation from. So first, let's just look at a Gen Chem concept. We know A plus B goes to C. So if we increase the concentration of A, or if we increase the concentration of B, we're going to drive that reaction towards C. Applying this to the enzyme and the substrate, just imagine that we have a beaker that we've just put in our enzyme and our substrate into, and we know that we're at the very beginning of the reaction, so the substrate concentration is going to be high, and because we haven't given it any time to proceed, we know that the enzyme substrate complex is going to be low and the product concentration is going to be low. So essentially, when we're coming up with the initial velocity equation, we can completely ignore this part of the reaction because it's so fast in comparison to the second half of the reaction that you can almost just think of this as the limiting reaction to determine the velocity. So we would write this out as if we were writing any other velocity equation. So this would be velocity initial is equal to K2 times the enzyme substrate complex. So you're often going to see graphs involving initial velocity, so it's important to understand how we derive these graphs. So the y-axis is always going to have initial velocity, and the x-axis is always going to have substrate concentration. So really what we want to see is how is substrate concentration going to affect the concentration of the ES complex? Well, when we're at low substrate concentration, you can think we're still going to have a lot of unbound enzyme. So if we continue to increase the substrate, we're going to be able to continue to increase the velocity linearly. So at low substrate concentration, the substrate is the limiting reagent, and the graph is actually going to be linear at this point because increases in the concentration will continue to increase the velocity. When we're at high substrate concentration, however, most of the enzyme is already in the bound ES complex. So you're going to get to a point where increases in substrate concentration no longer increase the initial velocity. So here our enzyme is actually going to be our limiting reagent, and our graph is going to start to plateau as we reach that point where increases in substrate concentration no longer affect initial velocity. And at that point we call it the Vmax. So now that we know a little more about initial velocity, we're going to describe a way to determine it quantitatively. So 3 things we already know. We know the equation for initial velocity, we know our steady state assumption in which ES is constant, and we also know the enzyme total is equal to the amount of enzyme plus the amount of enzyme substrate complex. So simply by putting these 2 equations together, we find a way to determine the concentration of ES, which is what we're going to need to plug in to determine the initial velocity. So we still have the equation that we just derived a few seconds ago, and now we're going to go over a few constants that we're going to end up plugging in to simplify the equation for us. So our first and most important constant is the Michaelis constant. By definition, it is the substrate concentration that gives us an initial velocity equal to 1/2 Vmax. When we're looking at this equation right here, this is actually equal to Km, so you can simply plug in Km right here. It's really important to understand what Km means in terms of affinity. So looking at these 2 graphs right here, we know that Km is equal to the substrate concentration that gives us 1/2 Vmax. So this would be Vmax, so we're going to call that 4. And so let's drop it down to 2. And we're just going to move over to our curve and drop down. So that is Km for the black curve. And then we're going to come over, and this will be Km for the green curve. So looking at this, we see that if we want to reach a velocity of 2, for the green curve, we're going to have a higher substrate concentration. That's not what we want. We want to be able to use the least amount of substrate possible to have our reaction proceed at the same rate. So here, Km is actually going to be better when it's lower, because this means that you're going to have a higher affinity between the enzyme and the substrate. So another constant we go over is Kcat. This is usually spoken in terms of turnover number. So it's the max number of substrate molecules an enzyme can convert into product per unit time. So if it's the max number, you know that it's going to correlate with Vmax. So this is our equation for it right here. In terms of general catalysis, which is what we're doing here, K2 is always going to be equal to Kcat because it is the limiting rate constant. So just thinking, turnover number, you know that a higher Kcat is better because this means that we can produce more product per unit time. So now that we learned a few more variables, we're actually going to derive the Michaelis-Menten equation just to show you how all of these come together. So we already have our equation that we put on the board before, but already put in Km for the rate constants that were there. So now we're going to combine this with the initial velocity reaction that we learned. And this is actually going to give us V0 equal to K2, enzyme total times substrate all over substrate plus Km. So the next step would be to add Kcat. So what do we know? We know Kcat is equal to K2 during general catalysis. So we can simply just take that out and put Kcat in there. So our last step to deriving the Michaelis-Menten equation would be to plug in Vmax. So Vmax is equal to Kcat times enzyme total. So by combining these two, we will get V naught equal to Vmax substrate concentration all over substrate concentration plus Km. So this equation right here is actually our Michaelis-Menten equation, and it's definitely important to memorize.